Welcome back, everybody. This will be your pre-lab lecture for the IR spectroscopy lab you'll be doing today. So IR spectroscopy stands for infrared spectroscopy. This will be your first introduction into organic spectroscopy methods to do organic structure determination, right? IR spectroscopy is very commonly used, and along with others, spectroscopic methods that you'll be introduced to in organic too, like mass spectrometry, UV-vis spectroscopy, and nuclear magnetic resonance, you'll be able to take an unknown sample and discern from its spectroscopic features what the actual structure of that molecule is. I mean, because think about it. If you're, synthesizing a molecule and you need to make sure you know what that molecule is, how are you going to do it? Well, we use spectroscopy and spectrometry as well. And you'll learn more about the distinction between those two words later. So let's go ahead and get started. Let me change the view. There we go. So recall that back when we were talking about plain polarized light, that light is made up of, light is made up of electromagnetic radiation, right? And electromagnetic radiation is composed of an electric field and a magnetic field. Those two fields are perpendicular to each other, and that's what composes light, right? There are parts of this wave that you need to know about, like the amplitude, for example. The amplitude is the height of a wave, right? And then there's also the wavelength, which is the distance between two wave peaks. Okay. You can also set an arbitrary time, right? Like say 1 second. Okay. And the number of times this wave travels in that 1 second, right? The number of waves that travel within that 1 second, between those 1 seconds, right? That single second, right, is called the frequency, for example, right? So here you have two cycles. Oops, I spelled cycle wrong. Cycles per second, right? And that gives you the frequency. Why do you need to really know those different terms? Well, it's because using those terms, you can determine the energy of the light. Okay. So here we have my old PChem professor used to always say, "What's new? C over lambda," right? Well, C here is the speed of light, which is a constant. And then this right here is lambda, and that's the wavelength. The wavelength, right? Same as this wavelength over here. Okay? And when you have the speed of light, which is a constant, and you have the wavelength, right? You divide the speed of light by the wavelength, and you get nu, which is the frequency. Okay, the frequency. Then you can take the frequency and plug it in over here in E equals h nu, right? And h here is Planck's constant. Not Planck's cont, like continued, but constant. And then you get the energy of the wavelength, the energy of the wavelength, the energy of the light, right? The light. So this equation here is actually, I think, called the Einstein-Planck equivalency, something like that. If you're a physicist, let me know, because I don't remember the name of this particular equation, right? But if you're, like I said, if you're a real good, if you're a physicist and you know what the name of this particular equation is, and you're watching this on YouTube, post the name of this equation down in the comments below. But I think it's like the Einstein-Planck something. I think it's equivalency, but I don't think that's right. There's something else wrong with that. Anyway, but yeah, so using those terms, you can determine what the energy of the light is. Okay, and why is that important? Well, that's important because the energy of the light, right, or the electromagnetic radiation, determines how it interacts with molecules. right, in chemistry. And so if you see here, notice here we have wavelength, right? And generally we do wavelength like, generally when we're talking about the visible spectrum here, which looks like a rainbow, visible spectrum, what was it, rho G biv, right? All the colors of the rainbow. That's in nanometers. That's on nanometer scale, right? So is UV, okay? But you can see here how all the way up here, right? The smaller the wavelength is, the stronger it is. Because here we have like gamma rays here, right? Coming from a star, right? And then we have X-rays here doing an X-ray, okay? We have somebody getting some white, like teeth whitening done right here, I think, with some UV vis, right? UV light. And then we have the visible spectrum, okay, right there, which is 400 nanometers to 700 nanometers. Okay, 400 nanometers to 700 nanometers. Notice again, as the wavelengths get shorter, right? That's what the small number is, right? That's 10 to the negative 12, right? The stronger it is in energy, the higher energy it is. And that makes kind of sense too, because that actually increases the frequency, right? That makes it so more peaks of the wave can fit in a single cycle, right? Right? In a period of time, for example. Okay? We have night vision goggles right here, which is IR, right? Then we have our routers and our microwaves. That's microphone, right? Microwaves. And then we have a radio over here, so that's radio waves, right? It turns out radio waves are the lowest, right? Energy, and it turns out that radio waves is what we use to do nuclear magnetic resonance, which is a very closely related to nuclear resonance imaging, right? That we do in hospitals. So let's go through a couple of these and see what kind of. But let's go through a couple of these and see how they actually interact with molecules, though. Okay. What's happening next? Oh, I didn't even realize that I had the the name of each of the sections of electromagnetic radiation labeled. So I guessed at these. No, I'm just kidding. I knew what they were. See, gamma, X-rays, ultraviolet, infrared, microwaves, and radio waves. Okay. So we'll move those over here, and we'll take a look at what each one can do. So let's first talk about gamma rays. I told you, like, gamma rays are super strong, like super strong. Okay. How strong are gamma rays? Well, turns out that gamma rays can make the Hulk, right? Gamma rays can make the Hulk. And so you'll see that the reason why is because gamma rays are so strong that they can break bonds, right? They can break bonds in your DNA and your proteins, right? And Hulk you out, right? And they can make the Hulk. Same thing is true of X-rays, right? And that's the reason why you have to wear lead vests when you're getting an X-ray done, right? Wherever you're not X-rayed. Okay, these people here will get all kinds of weird cancerous tumors and stuff like that if they were exposed to X-rays too much, right? Then we have ultraviolet light. And when you take ultraviolet light, and ultraviolet light is like 200 nanometers, 240 nanometers, 300 nanometers, around there, right? Let's just say between 300 and 400, okay, nanometers. That's ultraviolet light. And ultraviolet light, when you take those 2 to 300, 400 nanometers, right, one of those numbers between there, and you put it into the H equals, you put it into the what's new, C over lambda equation, right? And then take that frequency that you get from that and plug it into the E equals Planck's constant times E equals H nu equation. You actually get around 100 something or so kilocalories per mole, or kilojoules per. I'm sorry, not kilojoules per mole. Sorry, not kilocalories per mole. About 100 or something, 100 to 120, 150 kilojoules per mole. And if you recall back from when we were talking about dissociation energies, right, of carbon-carbon bonds back, when, I don't remember when it was, like last week or something, right? It turns out that ultraviolet light is the exact energy needed to disassociate a bond, a carbon-carbon bond, right? It's just around the same range, okay? Just around the same range. And that's why people get skin cancer when they're outside, being exposed to the sun and UV rays, right? It breaks the carbon-carbon bonds in their DNA, right? It makes these things called lesions right here, all right? And these are all examples of DNA lesions that can happen, right, when you are exposing your skin cells and your DNA, in turn, to UV radiation, right? And actually, let me actually, I didn't realize I'm blocking something here. There we go, right? There's the thymine dimer, right? That's not good. A dimer between the T's of your your ATs, right? Adenine thymine, right? So that thymine dimer. There's a spore photo product. There's a 6,4 photo product, and there's also a Dura photo product. All those things can cause all kinds of issues with DNA replication and translation, transcription and translation, eventual translation. When you do, let me say that again. All these dimers right here that are caused by exposure to UV light, right? Your DNA exposure to UV light can cause issues with DNA replication and transcription, and of course, eventually, translation of that, right? I mean, can you even get to the translation part if you can't even use your polymerase to go through and do replication and do transcription because the polymerase gets knocked off at one of those lesions? See, and that's the problem, and that's how people get like skin cancer. And so obviously, if UV light is strong enough to break the bonds between carbon-carbon, break the bonds, if UV light is strong enough to break the carbon-carbon bonds, X-rays is even stronger than that, and gamma rays is even stronger than that, and that's why you get the Hulk, right, from gamma rays. Let's get a little nicer now, all right? Then we have the visible spectrum. And so interestingly enough, right, the energy that's associated with the visible spectrum is lower than the energy of ultraviolet, of course. And so that energy is not strong enough to break bonds. Let me bring myself back. There we go. That energy is strong enough to promote electrons to a higher energy level, and when they come back down and relax, they actually release color or light in the form of different colors. And that's how we see and perceive colors. It's because white light, right, or sunlight or whatever, right, is being absorbed by these molecules, right? But the energy is not strong enough to break the bonds of the molecules like it is in UV. It just promotes the bonds to a higher energy level, the electrons in the bonds to a higher energy level, and when they relax down, they release that energy, that corresponding energy, right, that quantized energy, in the form of colors, right? And that's how we get colors of things like potassium dichromate, iron sulfate, cobalt cobalt 2 chloride, copper sulfate, and nickel sulfate, right? That's how we get colors. Right? The color of your shirt is because of this, right? It's because of this. And then we finally get to infrared. Okay? So this is actually a list of, This is a list of different organic/inorganic chemical spectroscopy methods that we use to determine the structure of different molecules, right? We have Mossbauer spectroscopy up here that we use to do, we use gamma rays, right? Actually, Mossbauer spectroscopy with gamma rays is used to determine the oxidation state of metals. Then we have X-ray crystallography. X-ray crystallography uses X-rays, of course. It's ionizing radiation, right? And like I was saying before, you're ionizing a bond, right? That means you're breaking the bond, okay? And X-ray crystallography can actually be used to not just determine the structure of molecules, but it can also determine the 3D structure of proteins as well, and enzymes, okay? And then we have visible, right, which is electronic excitation, right? And so you can use that, like I said before, to see colors and stuff like that. And so UV visible spectroscopy is based on seeing the absorption of the UV absorption of different molecules, or UV visible absorption of different molecules, right? Infrared, what we're talking about today in lab, right, is based on the vibrational transitions, right? And so that's infrared spectroscopy. And I'll talk to you about that more in detail in a second. Microwaves actually do rotational transitions. That's like Raman spectroscopy, all right? Raman spectroscopy. And then the energy that's associated with radio waves can only excite protons, and that's NMR spectroscopy. Okay? So from this point down, right? From this point down, you're not getting very much energy at all, right? In fact, the reason why we call infrared is because the lowest energy color is red, and infra means below in Greek. So infrared, below red, right? And the reason why we call ultraviolet is because the highest energy color, visible light we see, is violet, and above that is ultraviolet, and ultra means above violet. Make sense? So let's talk more specifically now about infrared spectroscopy. What is it good for? It turns out that it is incredibly good at identifying functional groups, literally in an instant. You put the sample in there, shoots the IR light in there, does a scan, and you've got it, right? And so Thermo Fisher has this cool little nifty handout that they give people that shows you what each band or each peak corresponds to on the IR spectrum, right? So you can see here, and we'll talk about how this works in a second, but you can see here, for example, one of the things that everybody knows is this here, this peak here at 1700, right, always corresponds to a carbonyl, right? Some kind of carbonyl compound, right? So it's right there, carbonyl compounds, right? Like an aldehyde is at 1730, a ketone is at 1700, an ester is at 1740, and a carboxylic acid is 1720. So you see a peak there, right? Between 2000 and 1500, around 1700. You know for a fact that you have a carbonyl compound present, right? A carbonyl compound present, some kind of carbonyl, right? And I forgot to say that the axis on a infrared spectrum, right? the x-axis is actually in wave numbers, or inverse wave number, so it's wave numbers. But what wave numbers are the inverse of centimeters, right? So inverse centimeters, right? You'll see that in just a second too. Just a couple more examples here. We have OH here, right? If you have a big happy face, or in this case it's a sad face, because it's a peak here, right? Over near the 3350s, you know you have an alcohol, right? Over at the 1100s, you know you have a single carbon-oxygen bond. And like you see, all these are listed here, right? There's a CH bond, right? Carbon-carbon double bond, carbon-carbon triple bond, rings here. We have rings here, like benzene rings. All the carbonyls, right? And then we have all the nitrogen groups, the amines and the cyanides. So literally, using IR spectroscopy, you could determine many different functional groups. Well, how does it do it? Well, like I was saying before, right? The amount of energy that's corresponding to IR light, right, isn't very strong. So it's not strong enough to break the bonds, right? It's not even strong enough to promote the electrons in the bonds to higher energy levels to produce color, right? But it is strong enough to make the bonds move around, like actually move, just move. That's all they're doing, right? And so they move either by stretching, scissoring, twisting, rocking, or wagging, right? But for IR spectroscopy, the most important is the stretching, right? The stretching, vibrations. That's the word I was looking for. The stretching vibrations. The stretching vibrations, okay? And so whenever you look at something like this, and we're looking at these numbers right here, we actually call them, for example, we call this a CH stretch, right? Or we call this a carbon triple bond stretch, right? And that's where the word stretch comes from when we're talking about that. It's because the most important of all the vibrational modes in infrared light in those molecules is the stretching, symmetrical and asymmetrical. So that stretching is so that stretching has a frequency, right? And that frequency corresponds to an energy using those equations that I showed you earlier in the pre-lab, right? And when you calculate what the energy is, it gives you these quantized, right, energy levels, okay? So, for example, if there's a large energy gap, right, there's a large energy gap, like this one here, we have a CH bond, right? We have a CH bond, okay? And then, oh, and I even have the equation right there, I forgot. You have a smaller gap, it corresponds to OH, a CO bond, right? A CO bond, right? So here we go, CO, right there, right? CO bond, okay? So this is just a very, actually, I'm blocking again. Here we go. This is a very simplified chart to show you where certain things are, right? So here between 4,000 and 2,700 wave numbers, and the reason why they did it this way is because instead of using wavelength, right, which is nanometers or centimeters, they did inverse so that the bigger numbers would be more energy now instead of smaller numbers being more energy like it is when you do wavelength. Because remember, when you do a smaller wavelength, you actually have a larger energy. So here, between 2,700 and 4,000 wave numbers, right, you have all the XH bonds, anything that's bonded to an hydrogen, right? And that's why this is a large energy gap right here, right? Because these are larger numbers. It corresponds that way because we're doing the inverse now, not doing the actual wave length, okay? And then on the other hand, we have a smaller energy gap over here, and then that's the single bonds between 1,600 and 400, right? And of course, here near the 1700s, we have our double bonds, but most importantly, we have our carbonyls, right? And our triple bonds are here between 23 and 2100. So the thing that you need to remember is that bonds to OH is this region, 4,000 to 2,700. The triple bond region is here, 2,300 to 2,100. The double bond region is here, 1,850 to 1,600, and then the single bond region is here, 1,600 to 400 nanometers. So how does an FTIR instrument actually work? Well, it's actually really simple. You have an IR light source, right? And it hits this beam splitter, right? And it goes, after it hits a beam splitter, it goes in a couple different directions. It goes to a mirror here, and it goes to a mirror here, which is not the important part because eventually it all comes back together again, right? And that IR beam goes through the sample. And when it goes to the sample, it hits the detector. And the detector can detect the IR light coming through in a couple different ways. And the way we do it in IR is we do it with transmittance, okay? So these here are all transmittance, right? What IR frequencies are being transmitted through the light. Contrast that with, for example, UV vis, where you're actually detecting the absorbance, which is the opposite of transmittance, right? But you should remember that. You should recall that from Gen Chem 2 when you're using those spectronic 20s to do, was that in Gen Chem 2 or is that in Gen Chem 1? It was probably in both Gen Chems, where you used the spectronic 20s to do, rudimentary spectroscopy. You were trying to discover the concentration of something using absorbance and the concentration curve, right? This is the same thing except opposite, because now instead of detecting the absorbance, you're detecting the transmittance. And if you really dug deep into what you were doing in Gen Chem, you actually had to take the transmittance number from the spectronic 20 and convert that into the absorbance number, right? So here the sample is sitting right there, the IR light comes through, and the detector detects the IR frequencies, right, or the IR stretches that are. Oh, I forgot to bring myself back. There we go. The IR stretches that are present as the light comes through the sample. Okay, and that's how you see an IR spectrum. Okay, so back in the day, we used to use back in the day. I mean, this was really back in the day. We used to use these little salt plates, these little salt discs, right? They look like little discs, like that. Really, they're called windows, right? And they're, for example, one of them could be made of like KBr, potassium bromide. Okay. And what you do is you'd have two of them, and you would sandwich your sample in between. Usually, it'd have to be like a liquid sample or something like that, and sandwich your sample in between. So there's my sample, and then there would be another KBr window on top of it. Okay? So now I have like a sample that looks like this. And it's in between two KBr windows. Right? And that's what actually would go into the sample holder. Right? With your sample. But that was so cumbersome. And I'll tell you why. I don't know how many times we had people that were using these KBr samples not realizing that KBr is a salt, and they would try to clean the KBr with water. And so when they cleaned the KBr with water, the KBr would start to dissolve, and it would leave it all opaque, you know, and like dissolving it all. And so like your KBr windows were like not clear anymore, right? They were all opaque. You couldn't do it good IR if your life depended on it, right? So they invented this thing called the ATR, and that stands for attenuated total reflectance. And what that is that it's a new way, or not? It's not new because it's been a while it's been here for a long time, but a different way, right? Where the sample actually sits on top of this crystal, right? It's a crystal, and then here's your sample, right there. Okay, the crystal is like made of what is the crystal made of? Selenium, I think, something like that. I can't remember what the crystal is made of. If you know, post it in the comments below. If you're watching on YouTube, and then so the sample sits up there, and it could be a liquid sample or a solid sample. That was one of the advantages of using the ATR, because the ATR had this thing at the top that was like an anvil, like a hammer thing, right? Looked like a microscope even, sort of. And what you do is you would twist this knob that was on the side, right? You twist this knob right here, and it would actually crush the sample into the crystal. It would crush the sample into the crystal. And then, so the beam of light, right? Say this is the beam of light right here, right? Going through all the same stuff as before, but now it goes into this crystal. And the top layer of this crystal is actually in contact with the sample. And so what happens is that the light goes into the crystal, like so, and it starts bouncing around inside the crystal. When it does that, it actually sees and goes and interacts with the sample, right? And it causes this thing called an effervescent wave. Essentially, after it comes out, it's gone through and sampled the sample multiple times, right? And then the light comes back out and goes into the detector. And it made IR spectroscopy so much easier, right? So much easier. Anyway, so that's attenuated total reflectance, okay? So for this lab, right, I think that's actually the last slide. It is. So for this lab, I guess I can come back. For this lab, you'll be getting IR. The video is actually very good, and it will go through the basics of using IR spectroscopy to identify functional groups, and you'll be getting some data, IR data, like spectra, right? And you'll be using that to identify certain molecules and stuff like that. So make sure you do your pre-lab quiz first, request the data on the report submission thing, and also look at the IR data too, and then just knock it out of the park. spectroscopy is a lot of fun. For me, it was because it's like solving a puzzle. You have all these pieces. You have an unknown molecule. You have no idea what it is, and you have all these pieces, right? Like IR spectrum, NMR spectrum, uh, uh, mass spectrometry, right? All these different pieces, and you put it all together to figure out what an unknown sample is. And I think it's a lot of fun, and you'll have a lot of experience doing it in organic too. And I think you'll have a lot of fun doing it too. All right, so good luck with that, and I'll see you guys for the next lecture.